Okay, starting on Chapter 5, Sections 5.1 and 5.2 can kind of be lumped together as a whole. I don't particularly like the way that Stewart progresses logically through these two sections, so I'm going to present it to you the way that it was presented last year and the year before, and hope that it makes more sense that way, and then try and tie it in with the way that Stewart presents it in the book and the way that your teacher is likely doing it. Now, this all ought to look very, very familiar, guys. We did this. This was section 11.5 in your book last year. It was the second to last section that we did. It was the section on limits. And we basically dealt with approximating the area under a curve and then applying a limit, and that's how the limits were tied in. Okay? So, in the interest of actually tying in what we did last year and trying to remind you of all of that, if we have any sort of curve, right? If we have something like this, okay, and we'll call this f of x, and we want to find the area under the curve from A to B, okay? Well, if we want to find an approximation, we need several things. First of all, we need the function, okay, or some sort of representation of it. We need the interval, which we will always refer to in these circumstances as AB, and we will need the number of subdivisions, okay? Number of subintervals or subdivisions, okay? So let's say that we want to find, an approximate area with 4 subdivisions, okay? That means that I need to break it apart like this, okay? Now that is 4 intervals between A and B. So A and B, and n in this case would be equal to 4. Now if I'm dealing with something like this, I know that the next question is, well, how am I going to gauge the height, right? Obviously, if I'm dealing with subintervals, especially if I'm dealing with subintervals of uniform width, which for the time being we're going to deal with, that is the width of each of the rectangles. Remember, I'm going to be basically using rectangles to approximate the area. And let's go ahead and say that the left-hand side of the subinterval defines the height. So I want to go up from the left-hand side, find the height, okay? I want to go up from the left-hand side and find the height. And so if I'm dealing with what's called a left-hand sum, the interval has a definitive width, and the height is determined by the function value, because that's what that is, right? The height is determined by the function value on the left-hand side of that subinterval, okay? And here we have it. Again, left-hand side, and again, left-hand side, and again, left-hand side, okay? Now what we're going to do is we're going to take the area of all 4 of those rectangles, add them up, and that is going to be the approximate area of that function underneath the curve between A and B. Gosh, that orange didn't really show up very well, but okay, I'll use another color next time. Now, we notice that this is probably going to be a pretty good approximation. If we eyeball it, we notice that this rectangle is a bit of an underestimate for that subinterval from here to here. We notice that this interval is a bit of an overestimate. Here's another small overestimate and sort of a moderate underestimate right here. And you can pretty much take this piece and fit it here with a little bit of leftover, and so there's just about as much overage as there is underage in terms of the approximation. So this is going to wind up by a happy accident, as it were, to be a pretty good approximation for this curve, okay? So as we move forward, we need to understand the fact that we're dealing with f of x on an interval from A to B, and we're dealing with in subintervals, okay? And that's going to be important for our notation as we move forward. Let's go ahead and progress to number 4 in your book, which basically asks for the area under the curve of f of x is equal to root x. And I've gone ahead and drawn this ahead of time. And we know what this function looks like. It's really easy. It's the parent of the square root functions. And let's say I want to estimate this as a left-hand Riemann sum, okay? And so what I'm going to do, and basically it tells me that it wants 4 subintervals, okay? N is equal to 4 on the interval 0 to 4. And that's all the information that you need, right? The function, the number of subintervals, the interval, and of course whether it's left hand or right hand or what's coming down the pike, midpoint. So what we need to do is we need to basically go ahead and draw this as a left-hand Riemann sum. Now, the first subinterval is going to be 0 to 1. And on 0 to 1, the left-hand side is 0. Okay, so the left-hand side determines the height of the rectangle formed within that subinterval, and therefore the height is going to be 0. Okay, so the first rectangle is actually non-existent. The second rectangle, however, has its height determined by the left-hand side of the 1 to 2 interval, and that, of course, has a height of 1. Okay? Now, the right hand, this third interval from 2 to 3 has its height determined by the left-hand subinterval. I mean, the left-hand function value of that subinterval, and which we know, of course, is going to be root 2, right? And actually, I did a pretty good approximation of that. That looks like about, it's going to be 1.414 is the approximation we know to 3 decimal places. And that looks about like 1.4, so we did okay on that. And of course, here on this fourth subinterval, I know that the left-hand side is going to determine the height. And if we remember that the function value is going to be root 3, and root 3 is approximately 1.732. And that's somewhere between 1.7 and 1.8, so we did okay on that as well. So we want to go ahead and sum up all of those rectangles. Well, the area of a rectangle is very easy to figure out. We know that because the interval is 4 wide, and we know that the number of subintervals is 4, the width of each of these is going to be 1. Right? That wasn't really hard to figure out. Okay. Now there is actually a formula to help us with this. It's actually pretty intuitive. If I want to know the width of the subinterval, something that I'm going to in the future refer to as delta x, I simply need to know the width of the interval, which is of course b minus a, and then I need to divide it by the number of subintervals. In this case, that would be 4 minus 0 divided by 4, or 1. Now, I know that the area of this first subinterval is 0, the height, times 1, the width. That's the area of the first one. Then I need to add it to the height, 1, times 1, the width. And then I need to add it to root 2 times 1. And I need to add it to root 3 times 1. Okay? And that is going to give us, and I'll go ahead and try to use a better color. Hopefully the green will show up a little bit better. That will be what the left-hand Riemann sum actually looks like. Okay? Now, we can go ahead and actually figure that out. It's 1 plus root 2 plus root 3. So if we break out our trusty calculator, okay, and we say 1 plus root 2 plus root 3, we're going to get approximately 4.146. Okay? So 4.146 is the approximate area, 4.146, the approximate area under the curve. Now notice that this approximation is going to be an underestimate of the approximate area. And that has to do with the shape of the curve. Okay? And so basically if we're doing a left-hand Riemann sum and the curve is increasing and concave down on the whole interval, it's going to be an underestimate, okay? Now, let's say that we were asked instead for a right-hand Riemann sum of that same function, okay? And we'll go ahead and mark it off like we did on the last one, okay? Now, let's go ahead, and we know that on this new subinterval right here, let's go ahead and state it explicitly. It's on the intervals 0 to 4. We're dealing with 4 subintervals, and we're dealing with a right-hand Riemann sum, okay? So we want on this subinterval from 0 to 1 for the height of the rectangle we're using to approximate to be determined by the function value on the right hand of 0 to 1, which means the function value at 1, okay? From 1 to 2, I want the function value at 2 to determine the height. From 2 to 3, I want the function value at 3 to determine the height. And from 3 to 4, I want the function value at 4 to determine the height, okay? Now, obviously, these have the same width, right? So these rectangles are all still 1 unit wide, and so we're going to get 1 times 1 plus 1 times root 2 plus 1 times root 3 plus 1 times root 4, but root 4 we know as 2. Okay? Now, this looks absolutely identical to the last sum, right? Because, you know, this was identical to the rectangle in the second subinterval. This was identical to the rectangle in the third subinterval, and this was identical to the rectangle in the fourth subinterval. And so I basically just slid all of those over and added this one right here. So I know that this sum right here is 4.146. So this whole thing is 6.146. And I noticed just by looking at this Riemann sum, the pictorial representation of it, I know that this is going to be an overestimate. So I have one underestimate that gives me a sum of 4.146. And I have one overestimate that gives me a sum of 6.146. So I know that the actual sum, the sum that I'm sort of trying to get at by these approximations, is going to be somewhere in between, okay? And we'll know soon enough how to actually get it exactly. We have a method of getting exact ones by use of limits, but that's sort of reserved for polynomial Riemann sums. Now, I hope that this actually brings back a little bit of memory and recollection from our discussion of Riemann sums. In the next video, what I'm going to do is we're going to basically talk about a couple more examples, and we're going to talk about left hand, right hand. I'm going to introduce midpoint Riemann sums, and we're going to talk a little bit about notation. From there, we're going to move on, and I'm going to reintroduce finding polynomial approximations, not for a particular number of subintervals, but for n subintervals. And that way we can go ahead, take the limit, and find the actual area. One new thing I am going to introduce in a couple of videos hence is going to be how do you deal with Riemann sums and approximate areas when you're not given an explicit function, when you're just given numerical information, almost like tabular data, which they're very, very fond of doing on the AP exam, so we're going to talk about that as well. But that sort of brings us to a close on video 1. I don't know exactly how many videos we're going to run through. We'll just run through as many as we need to in order to get 5.1 and 5.2 under our belts. Okay? So be looking forward to that.